So we're going to continue talking about analyzing 2x2 tables. Go beyond the 2x2, the two-dimensional tables, row and column thing. There were also a little bit of homework 9 questions. How about homework 9 is a tables material. Right, but the beginning part of it has to do a little power and then a likelihood ratio. So, questions about the?
Yes.
Yes.
On the final part of question 2.
Okay. So in 2, we're doing
Likelihood ratio.
Of likelihoods.
Aren't those two equal? X to the 1/4 equal to square root x. Aren't those equal?
Yeah, these two things should be equal. Yeah.
They are the same thing.
Right. Yeah. It's like x to the 1/2, x to the 1/2. So anyway, what is x to the 1/4? So I don't know. For some reason, I thought, well, that's the square root of this. Square root. I mean, just kind of illustrating what is that? What is that thing? It's the fourth root of something. So if we had 16, the fourth root is 2, and so on.
Gotcha.
Yeah.
Can we just like set up to? I was just confused, like following. And like
Right.
I got like the likelihood of theta 0 over likelihood of theta A, and then I didn't really know what to go.
Right, right. So to set this one up, this is a, so on the homework 9 thing, on this, setting up the ratio, the density was this theta x to the theta minus 1, right? And then x is between 0 and 1, and the theta parameter is just some positive number. This is actually a beta distribution, a certain beta. And so there's null hypothesis that theta is 1/2 versus that it's 1/4. Right? And so the likelihood ratio is the ratio of this likelihood at these two points, right? So if you have 1/2 in the first one, there's an x to the 1/2 minus 1, and then 1/4 x to the 1/4 minus 1.
So you get 2x to the 1/4.
Yeah, so 2x to the 1/4, right?
Has to be less than c.
Less than some number c. And so we're going to go through the business of looking at the power to try to figure, or the type 1 error to try to figure out what c should be. So it asks you there to rearrange it, right, to get x is less than something, right?
X is less than c to the 4th over 16.
Yeah, if you raise everything to the 4th, so 16x is less than c to the 4th, rearrange it, and you get c to the 4th over 16. Right? And we're going to choose this thing so that the probability we reject, right, is only 5%. And so that's where that integral comes in. The probability, under H0, the probability that our random variable is less than or equal to some cutoff is, some number is just k, just the square root of whatever that number is, right? That's what it says there, right? And so we want the probability that x is less than or equal to c to the 4th over 16 to be 5%. Because if the null hypothesis is true, we don't want to be less than that cutoff more than 5% of the time. So what's this? Well, that's the square root of this thing. Oops. It always messes things up. So square root of this, right? You want that to be 0.05.
Square both sides.
Right. And so then that you can solve for that to get a value of c, and that's your cutoff.
What do you do on this next?
The next part
Is instead of doing square root, you do 4th root?
4th root, yeah. If, so that gives you a cutoff. That gives you an x, an x value here. But now you're going to say, what if theta is actually 1/4? What's the probability you do reject when theta is 1/4? theta equals 1/4, the probability that x is less than some cutoff number is going to be this number to the 1/4. But the square root, right? And so we get cut off. We get the cutoff from earlier. The previous page, put it in there, and then compute. And this is the power, right? Because we reject when our x value, our random number, is actually less than that cutoff. Right? So that's a likelihood ratio test with one observation. Does that help clarify a little bit of that?
Very much so.
Wait, and you still set that equal to the...
The thing we got from before.
So whatever our C value is then?
Yeah.
Okay.
You get the C this number.
Gotcha.
Ends up being in there. So. And when I calculated it, power looked pretty small. Like, there's not a lot of good chance of distinguishing two numbers there.
Thank you, sorry.
And then in part 3 is a simulation. Because you can simulate data under simulation. So f of x is the density in observations. So x is the data, that could be 5 observations in the simulation, and theta is whatever we choose. And so you run this, well, okay, let's see, if I start here, then that defines the function. Now this fx is the probability, oops, wrong screen. That fx is this function. So if you put in, fx, if you put in 0.2, 0.5, 0.2, get those three things, then theta was 1/2. It'll give you that likelihood value. If you put in 1/4, it'll give you that value. Because it's taking, say, 1/2, now there's 3 in my little example here. And then the product of those things is 0.2 times 0.5 times 0.3. And all of that raised to the 1/2 minus 1. And so that gives us, for instance, that first number. And so this is going to do something 10,000 times. Create a likelihood ratio, which I like to call the capital lambda. I'm calling it lambda 0 because it's under the null hypothesis. So I'm going to generate 5 observations here. It's a random beta with 1/2 and 1 as the two parameters, actually. The theta is that. So I'm going to generate 5 data points, calculate this density under 1/2, time divided by the density at 1/4, the two parameter values. I can see what those things look like, look at the 5th percentile, because we reject when it's small, so looking on the small side. And that's the cutoff that we're going to get. And then we're going to generate data under theta equals 1/4 and see how often do we actually reject under that. So it's a little bit of coding, but that simulates the thing. So if you run the whole thing, define our function, set up b, send to lambda 0, run, here's the histogram. That's the values there. The 5th 0.31 is actually the 5th percentile, so if we got a ratio less than 0.31, we would reject. So I call that cutoff. Generate a bunch of data, 10,000 data sets when it's actually 1/4, though the alternative is true. Those histograms look a little bit different. They're a little bit more bunched up towards 0 because it's smaller. How many are actually less? Well, about 50% in this simulation. Right? It's a lot better power than the numerical result that you got in part in the previous one, because it's 5 observations instead of 1. Right. So there's a pretty big difference between those beta distributions. So you can, we're trying to decide, so do a histogram, we can do a random beta, let's do 10,000 values. If 1/2 1, here's the null distribution. and here's the alternative. It's a little flatter, right? So if you kind of toggle back and forth, you can see how much of a difference there are between those. And one value, yeah, both of them are going to tend to produce things that are pretty small. So one observation is pretty hard to tell. But once you have 5, you know, you're not going to get, maybe you get one of them out here under the alternative, but under the null, maybe it's 2 or 3. So, you know, it's just more likely. So that's the likelihood. Any other questions? So we're going to do more with the tables today, right? And that should help with doing the final problem. We'll talk a little bit about the end of chapter 10 on Friday, likelihood ratio test for tables, and a general use of goodness of fit for tables. Right? Good.
Okay, so we're doing, so in chapter 10, we're looking at two-way tables.
So we have a table that could be called an I times J contingency table. You might also call it a table of counts. And so it has I rows, J columns. And we put it in a table here where 1, 2, down to I, and 1, 2, up to J columns. And the number that shows up in one of these things is either called Xij. The book uses N. This is the count of units or observations or survey members or whatever that are classified in row I and column J. And so this is the observed count that we get from cross-classifying our responses according to two factors, the row factor and the column factor. Right? And then we have hypotheses about, are these variables related to one another? So this is a two-way table. And of course, you could go with three-way, so four-way tables. You wouldn't picture them so much here. But a three-way table might look like a cube, and a four-way table might look like a series of cubes. Right? And so that the area of categorical data analysis fits things called log linear models that express the expected values under fairly general models, and they get kind of complex. So this is kind of the broader area of books and so on. It's called categorical data analysis. And it looks at all fancy types of things, relationships between variables. The basic hypothesis we're going to do is, are these independent of one another? Or if one of these, say the rows, are more states of nature that you really can't manipulate, do we get different responses? And do we have the same proportions across the columns for each row and so on? So there's a homogeneity of proportions we'll also do. So the hypothesis basically we will do is the null hypothesis says that the row and column are independent of each other, which would mean that the membership in a row and column, given that you're in a certain row, it doesn't really influence which column you're in. Or if you're in a particular column, it doesn't influence which row you're in. So the rates of being in the row is the same for all the different columns. Right? And so the null hypothesis could be if Pij is the probability in being row I, column J, can be written as the probability you're in row I times the probability you're in row J. Right? And that little dot means it's added across the other dimension, right? Or averaged across the other dimension. Another way that this might be done is you're in the ith row, kind of with the superscript, meaning that rows and a column. Right? There's if you look at textbooks and things that deal with this, with tables and things, they make up all sorts of notation to do this. Maybe they call this plus, So this is the probability of row I for either one of those two things. And then these two here could be read as the probability of a column. This is R, column J. So if they're independent, the chance that two things happen together is just the product of the two things independently. Right? The alternative is not independent. So some deviation from that. Some rows and columns have extra comparison to what you would think under independence, and some others have less. And so there's just a discrepancy under there. If they're independent, we can calculate how many of the n respondents would fall into that cell, be cross-classified into those two things. Right? So expected counts. Under independence. In general, the expected value is the number of subjects we have times the probability. But under independence, it becomes n times the row probability times the column probability. And we're going to estimate that by putting in the sample. We're going to estimate the number that are in that row by the count across the row divided by n. And the chance that you're in column J is we're going to look at the number of people that are in column J divided by that, and one of those n's can cancel. So it's often presented like this, which sometimes can hide the fact that it's n times two probabilities that are being estimated, right? And so sometimes, the observed count sometimes it's given, sorry that there's multiple ways. The book calls it either x or n for the number, but this, observed, this is the data, that's the actual number that's there. And this is the expected count. And maybe this is called EIJ here. And so we're going to evaluate this hypothesis. If the observed count, however you give it a notation, is close to the expected, we're not going to reject independence. Right? But if there's too much of a discrepancy, right, if some of these counts are quite a bit higher and other ones are quite a bit lower, it has to balance out, right, to add up to n overall, then we just can't believe independence. Right? So we need a statistic that compares all the cells, puts this all together, and then a reference distribution. Right? We're going to calculate a statistic and then see, is it very discrepant? Is it, in this case, is the difference, kind of a square difference, is it very much large in comparison to what you would get by chance? Right? So the chi-squared statistic, usually called x squared, the book gives it a value of c, which is the sum over all the cells in our table of the observed count minus the expected count squared. Right? So some of them are positive, some of them are negative. Some of the differences would be 0. So we square them, make all the differences here, and we standardize them by the expected value. Right? Underlying this is, if the counts have Poisson random variables, like Poisson counts in every one, then the variance of a Poisson is like its expected value. And so its standard deviation is like the square root of its expected value. So in a way, this is taking the observed minus expected over its square root, kind of creating a standardized z-score, and then squaring those things and adding them up. Right? If the expected counts aren't small, none of them are less than 5, or in larger tables, fewer of them are less than 5, then under the null hypothesis, the x squared has a chi-square distribution with a certain degrees of freedom. And the degrees of freedom depends on the size of the table. And it's the number of columns, or number of rows minus 1 times the number of columns minus 1. So the number of cells is I times j. But there's some restrictions in there. That has to add up to the total sample size once you add up all those. All the proportions add up to 1. Further, the proportions by column and proportions by row add up to 1, right? So in this I by j table, once you know the outer margins of what they add up to, you don't actually have to fill in all the rows and columns. You do fill in I minus 1, and then the last one's determined. And you go j minus 1 this way, and then the last one's determined. So there's really kind of I minus 1, j minus 1 independent choices in there, right, to filling in the table, and the rest has to add up. Right? And so if our x squared is large, right, we're going to reject the null hypothesis. Right? If our x squared statistic is greater than this chi-square, the upper 95% with this degrees of freedom. If it's not, then we can't reject it, and it's not quite inconsistent with, statistically not inconsistent with independence. When we had 2 by 2 tables, this was 1, right? So that's what we had before. It's 2 by 2 table, once you fix the margins, all you have to do is pick one number, and then the rest have to add, and then the next has to add, and so on. The other ones have to go. But if it's small, smaller sample sizes, larger tables that are a little more sparse, this chi-square approximation it's kind of based on normality, right? It won't work so well, right? So we can do a permutation. To do this, we're going to create, well, how you would do this is you could create a data set that has measurements for every individual, right? And so you can have one variable that defines the row variable, right? And this is the column variable. And every person there, say person K here, has a row and a column value. So for each person, we know what row they're in. If this is race ethnicity, we know what race ethnicity group they are. And if this is some measurement of else, some type of score, or some health measurement, this is categorized by the health score, right, in terms of level of health. And we would know that for everybody. And we take that information and then we make our 2 by 2 or I by j table. So if things are independent, right, this pairing is just by chance, right? We might as well have R sub k paired with some other value from that set there, right? And so we're going to randomly permute the columns, right? Calculate the statistic again, and once we do that thousands of times, we can compare our actual statistic we got to that and get a p-value through simulation. We'll do some examples today or both. Right? So let's look at these with some numerical examples in R. The problem 10.8 that we used last time had boys and girls in rural China. They're shown advertisements and asked to give their impression of products. And the children reply that they like the products very much. They like them. They neither like nor dislike, or they dislike them, or they dislike them very much. And so we end up with this 2 by 5 table. 2 by 5 table. And we could ask the question, you could summarize, do they like it or not for the different products? Overall, you could look at boys alone or girls alone. But we also want to ask the question, are these variables related? Does opinion seem to vary by gender? Right? So the numbers are 180, well, 725 boys and 755 girls. The problem says 1481 children, and in their table I only count 1480. So I think somebody just didn't answer some question. This was 260, 137, 96, and 52. And among the girls, there was 210, 266, 145, 85, and 49. And so adding down the rows is 390, 526, 282, 181, and 101. So the hypotheses are going to be that these two variables are independent, or really that the rate of liking, the proportions of liking and not liking are the same in the two groups, right? So let's look a little bit at R, and we can talk about how this goes. So, going over this one, remove everything that's in my data sets. So I'm starting out here just with this empty environment, and I'm going to set up a matrix, MAT, shorthand for matrix, that has the row for boys and the row for girls. When I showed you before, I did a matrix command and set up all the data and tell them how many rows. The book uses this command called rbind. There's row bind, where you stack things on top of each other, or there's column bind, cbind, where you stack columns together. So I can just put a whole column, a row that is boys, my counts of boys, my counts of girls, and put them together. And that's just something about the graphics. And so now I have this matrix here that has boys and girls, and I took the names I gave them. There I can add column names to it. So just like very much, like, neither, dislike, dislike very much. In that order, I can put that there, and then I get the labels. Makes it a little easier to see. Right? What are the row totals? This apply thing is useful here. The other thing you can do, take the matrix and take the first row and add that up, and that's the girls. Or the second row and add that up in the boys. There's a couple ways to operate with that. The column totals is this command, so it's going to preserve the second dimension, the column dimension, and add down there. So for instance, if you did the sum of the matrix, the fourth column, it's going to be 181 for the dislikes. And the whole total is 1480. Before we jump to doing expected values, you can describe things. The column totals, if you divide that by the 1480, oops, yeah, there's this that block in there. Oops. That thing divided by 1480. There's 26% that liked it very much, right? 35.5% that liked it, 19 neither, 12 dislike, 7% dislike very much, right? For a report, you probably round that to a decimal place or two. For that, those are the overall ones. You could take the matrix, like say the first row, which is the boys in this case, and divide it by how many boys there were, 725. Their percentages are like this. This was every boys and girls together. There's not a whole lot of difference, right? I mean, there's a 1% difference there, but that's not huge. What do the girls look like? So the girls had like very much, or like a little heavier, a little higher.
Shouldn't you divide it by 755 instead of 725?
Oh yeah, right. Yeah, you want the number of girls, right? So you want it maybe more appropriate, right? Get the right denominator there. And then it's not quite as different, but it's still a little bit higher. But is that enough to say that these things are different? That the distribution for boys and girls is actually different? To do that, we're going to calculate expected values. It's a chi-square test command that will give you expected values. So where did some of those numbers come from? So it's just right underneath this. These are the observed counts, right? So to get this first 191, right, we're going to take the column total here, 390, and this row total, the 725, and multiply them together, and then divide by the 1480. And that's what the formula says to do. And so we're going to do expected values, our computation, right? Oops. No, it's one more. Right, this is the computation we do for the expected. We have to do it for all 10 of those entries. Up and down down within each column, they have to add up to that total. So actually, if you really have to calculate only 4 of them, right? And then the others have to add, and the others have to add. So if you're doing it by hand, and you realize that they have to add, you can save a little bit of time. The expected calculation here. So first row, first column. The first row had 725 boys, and then it had 390 liking very much, right? So like very much, and boys, right? And then the 1480, and that would give that first
191.
191. And I would keep, yeah, keep
0.04.
0.04. Keep some decimals there, right? Because if you round it to 191, another one, say it had been 191.4, it's going to make a little bit of a difference in the accuracy. So keep a decimal place or two. Expected values are not necessarily integers, right? Although these are people, we understand what we mean when we say we have, households have, 1.2 kids on average, right? Nobody has 0.2 kids, right? But some have more and some have less, and you just average those integers together, and you get that, right? So you do that for all of them, and you get these expected values. You could kind of automate it, like you take the entire, these are the sums of the columns. Right? So you take 725 times each of those column values, and you get the entire first row all at once. And then 755 for the girls times the column totals. And you get these numbers. And so those should match those up there. So if you save all these and save all those others, we have to calculate that statistic. So each of these numbers, right? 180 minus 191 squared divided by 191 gives that contribution. There. There is another part of this chi-square test. There is a residual. These things are those statistics. So if you take, what was the observed number there was 180. 180 minus the expected 191.04, and you divide by the square root of 191.04, you get this so-called residual. And there's a little bit of rounding there, so it's pretty close. Right? Kind of this. The thing you add up is really the square of that. So we would add up the squares of the residuals. Those are all the residuals squared. Right? So 180 minus 190 squared divided by expected is about 0.638. A little rounding there in the third decimal place. Those are each of those contributions. There's 10 of them. Right? We add up all 10. Right? And so adding up those square test squares, you add those things up. Okay, there we go. Get 2.75. If you do this whole test thing here, you get 2.75 as our statistic. This correction, there is a continuity correction that can be applied because you're going from discrete counts to kind of a continuous chi-squared, just like going binomial to normal. You can add 1/2 to certain cells. If you don't do that, you get 2.75. Degrees of freedom is 4. Right? So we had 5 minus 1 times 2 minus 1. So there's 4 independent choices there for proportions. And since the p-value is 0.5998. So it's not unusual. Right? It's not surprising. Right? So we would not reject independence. The expected values that we saw, wherever they were, the data and the expected values, there are some differences. They differ by 10 or even a little bit more. But relative to the number count that's in there, it's not a big deal. So they're pretty consistent. When we look at the proportions, They were, within 1% of each other generally, or a couple percent. So not such a big deal. So we do not reject independence. The boys and girls might have the same opinions about these ads. Where do they get some of this stuff? The 95th cutoff for this kind of square distribution is 9.49. So if we got a statistic of 10 or 11 or 12, right? If you think about it, there's 10 cells. Each one had contributed a residual of about 1, and we'd added those up, we would get something big. Or if one of them had a residual that was more like 2, that's the square root of 4, add up a couple more of those that are highly discrepant from that, and you're going to get a significant result. The p-value is the probability that we're greater than our statistic, greater than 2.75, under the null hypothesis. And so the chi-square distribution, its picture, kind of go to the end of what we have. The chi-square, once you get past a couple of degrees of freedom, it does go down. The chi-square 1 would shoot back up. The chi-square 4, chi-squared 4 looks something like that. And it says 9 something as a cutoff value up there. 9.449 has the upper 5% tail, right? So if we're anywhere out past that, it's unusual under that comparison, that reference. Right? We got, 2.5 something, 2.75, right? Back over here, and that had more like 51%, or no, 59%, so about almost 60% of the area going to the right. So it's right in the middle, very consistent with independence. No reason to get alarmed. To do the permutation, there's actually a simulation version of this. Right? If you can simulate the p-value, tell it true, and you can tell it the default is 2,000 replications, but you can make it more if you want. And so it calculates the statistic, does the simulation just like we described for permutation tests, and gives a p-value. And here I got a 0.59. There's some randomness to it. Oops. It went on, it didn't repeat. If you repeat it, you get other p-values that are kind of in the same range, but they're based on 10,000 randomization. They have the same message. It's not really different from independence. Now we look at one other data example. Back in the 1980s, that's the homework line, close that. Close that. The smoking industry lost lawsuits and had to pay billions of dollars because they were judged to have hid the fact that smoking was addictive and caused cancer. And they had memos from tobacco companies saying that, and then they still promoted it. So they had to pay billions of dollars to the states, probably not unlike the size of the opioid epidemic and those things, but maybe larger in today's dollars. And then with all that money coming in, it was used for healthcare, but it was also used for education and for other purposes. And there's an evaluation part, right? You're going to get that money and spend millions and millions of dollars. You're going to evaluate what it does. You're going to monitor tobacco sales. You're going to do surveys, and the Gallup organization did some surveys in a handful of states related to this, and this was a survey of smokers in California. They also surveyed non-smoking adults. So okay, that's what this one is here. This is a subset of the data. Male and female, age of the adult, the number of kids living at home, a variable called salience, how relevant or how much of a concern is teenage smoking as a problem in your community, rated kind of on a scale of 1 to 5, with 6 being don't know and 7 being refuse, or a set of other categories. How much people smoke, days smoking per month. Sometimes they wouldn't answer the question. Number of cigarettes per day. Would you like to quit? 1 being yes and 2 being no. Have you tried to quit? And things like that. The salience, just the smoke that it's in there, salience. 2, not serious, somewhat serious, serious, very serious, don't know, and refusal. So there's 4 levels actually, and then don't know and refusal are put in there. And so we can look at if some things are related. We have one thing that we might look at is a person's desire to quit, their stated desire. These are self-reported smokers, what they say, right, on a phone interview. Is it related to the number of children in the household? Right. There's a few complications to dealing with this. Here is, so let's see if we can do the variable like to quit. Here is 1 or 2, so 1 means yes, 2 means no. So a majority of the smokers actually say they want to quit. There is something hidden in here. Use and equals always. There are 75 people who didn't answer that question. Right? So what do you think about them? Right? These are smokers. You're asking them a question. Would you like to quit? Have you tried to quit? The whole environment is, it's after the legal judgment of the tobacco company. Maybe they don't want to say over the phone. Maybe they don't know. Maybe they haven't really thought about it. So they're undecided. But maybe they would like to quit. Maybe they don't want to quit. And they just don't want to tell anybody. So it's a little hard to know what to do that. And unfortunately, it's kind of a small percentage of that. If 50% of the people didn't answer, that question would be kind of almost useless, right? But you still have a pretty good number there. The distribution of the number of kids, so it's self-report. How many children under the age of 18 live at this address, right? And so here's a histogram, we can get that, of the number of kids, right? And the table of the numbers. 819 said 0. Some said 1, 2, 3. But there's a few responses that got typed into the computer that are pretty big. So what do these mean? Are these typos? 10 could be true, right? I met families with 10 kids. Right? But 21, 23, 24. What's the circumstance? Could that be a real answer? Could they be living in a community home and somehow have that many kids? Is there a group home? You call enough people, you're going to get somebody that answers that. But 44, maybe the number, the key got stuck, and it's really 4. 21, 23, those could be 2 keys hit instead of 1 because they're right beside each other. If it's at 17, you can't hit 1 and 7 very easily with one hand or something like that. So you just don't know, right? What it is exactly. You're kind of left with the choice. Do you throw out, there's really kind of 3 discrepant observations that kind of makes you wonder, right? And so maybe you throw those 3 out. It's a small portion. 10 people didn't answer. Could the people not want to admit to talking about smoking while they have kids at home? Something like that. So tough questions like that. So what did you make a table, right? And so also you get very small numbers, counts, 9, 2, 1, 1. But it's hard to do much statistical analysis with small counts like that, right? Maybe they want to quit, maybe they don't, but there's not much of a pattern. It's really just looking at individuals. So let's create a category that has 4 levels. Right? I'm going to use 0, 0, 1, 2, 3, and then 4 or more. Right? And so I'm going to copy over kids to a new variable called kids4. If it's greater than 4 and not missing. So when there's missing values, it will kind of make things happen funny. So I'm not really aware of better ways to deal with this, but this says if it's greater than 4 and it's not missing, I'll call it 4. So I think in every statistical software, there's an issue of how it handles missing values and what you do about it. So there's that. If it's 2 or 3 and it's not missing, I'm going to put it 2.5. I could call it 2, could 3. I'm not really going to use these numerically. They're going to be categories. So, and so here's my new table. Well, here's kids4 versus kids. Right? Oh, here's kids4, 819, 215, 291, that was the number 2 and 3 added together. And all these others add up to 44. 44 had 4 above, not counting the missing. And here's how they correspond to the original data. These categories were left, 0 and 1 were left. 2 was really 2 or 3, added together, these added up to the last one. So I've created categories that have a reasonable sample size in them for kind of checking independence or difference of opinions, and so on. I'm going to create a table here. That's the number of kids versus liking to quit or not, right? So 1 is like to quit and 2 is not under this. So there's that. What percentage?
You didn't save it as a variable.
I didn't save.
The table as a
Oh, the
variable.
table as a variable. Okay, yeah, I better. I might want to. Oops. There you go. So it's there now. So I could look at the proportion, of those that in the first row they want to quit, right? And so 67% have no kids, 78% have 1 kid, 77 have 2.5, 2 or 3, and then 86 have 4 or more, right? So the desire to quit seems to go up, right, with having more kids. If you look at the other way, right, it would go down. If you take the second one, these are do not want to quit. That's going down as you have more kids. So people with more kids report anyway wanting to quit. They also ask if they try to quit, and it's associated with that too. So there's 212.95 in this table. There's 84 who were either missing the number of kids or their desire to quit. Some were missing both. Right? The expected counts that we would get, let me put that in that here for kind of a quick comparison. Right, these are the expected values using our expected value calculation under independence. These are the observed ones. Right? It's kind of tracking it in some ways, but there's a little bigger discrepancies, I guess. Right?
The 4 on the not wanting to smoke is pretty big.
Yeah, this is 29 and almost 30 and 12, but it's 36 and 6. Right? This one's 77, but only 61 here. These are, there are some differences. The differences you'd expect to get bigger as you get bigger counts, just because you get a little more random variation there. But is it significant? Those are the expected counts. The residuals, now each of these has just 8 cells. Some of these contribute a residual that's already 2 or 3, and the thing that gets added together is the square of those. Right? So if you square those things, you're adding in 2, 5, and so on, because many of those are discrepant with the right there. So we do the test. You get a chi-square value of 20.4. Right, 3 degrees of freedom because it was 2 by 4. So you do 1 less on each, so 1 times 3. And the p-value is very small. So this suggests that there's a strong association between wanting to quit and the number of children present in the household, self-report by the individuals there. So yeah, we reject independence and think that there's an association for this one. Kind of interesting if you think about what that would mean, right? Right. But any questions about it? Categorical data analysis might go on and fit an ordered relationship, right? This is a test for a model that says it's increasing in a certain way because we see the increasing. So there's more you can do about characterizing that, but you could take a whole class on that. If tables are small, meaning small counts, you might have a very large table in terms of rows and columns, but the counts are just kind of small. So the chi-square approximation wouldn't work so well. Besides simulating p-values, there's a procedure called Fisher's exact method. And so the way that this works is, say you have a 2 by 2 table, and you have counts in there. And this adds up to A plus B, this adds up to C plus D, this This is A plus C and B plus D. Right? And so that's the table that you observe. Right? Conditional on the margins, the probability that you're in, conditional on these margins all around here, the chance that you have this configuration of the counts inside follows a hypergeometric distribution. For those of you who have taken probability theory, a hypergeometric distribution is often talked about having balls in an urn, where you have an urn and you have so many red balls and so many white balls, and then you pick a certain number and then classify them, right? And so the probability that you have this table, A, B, C, and D, given those margins, you have A plus B in that row, and then A are selected here, right? And you have C plus D in this row, and C are selected there. And that's divided by, you have N overall, and you've chosen a certain number to, I think, A plus C, is that A plus B? Right? So you divided so many into this first row. Right. And so kind of that ends up being the probability of that table. And so if these are red balls and these are white balls, and you're going to pick A plus C times, what's the chance that in your sample of A plus C you end up with A and C? So anyway, it has a certain probability, right? And so let's say we had a table that had 20, which number did I say? And 10, 2 by 2 table, and 15 and 15, so there's 30 here and 30 here and 60, and these add up to 35 and 25. Right? The probability of this particular table that we have under that hypergeometric, we'd have 30 choose 20 and 30 choose 15 following the notation, and then there's 60 choose 30, 35, maybe A plus C is supposed to be there. Yeah, I think it's supposed to be A plus C. It's here. So we're picking that many. So I think I wrote that wrong there. It's a little, right? But if you do this calculation, you get something like 0.8977. Right? So that particular table would have a certain probability. Right? And so what you can do is look at all the possible tables that could happen with these smaller sample sizes. So for instance, if you had, instead of, this is a little bit skewed to a little bit more over here and a little bit less here than you would expect under independence, right? A little bit more up there. Well, you'd have this, but you could also have something more extreme. What if you had 21 up there? Instead of 20. If the margins are fixed, 30, 30, 35, 25, then you can fill in the rest of the table, right? This has to be 9, this has to be 14, and this has to be 16. And you can look at the probability of that table. What's the most extreme we could get?
30 and 0?
Yeah, you could get everything, so that's one table. You get it. If you got 30 here and 0, is that possible? So then you'd have to have 25 here to add up to the 25.
And 5.
And 5 here to add up to 35, and then add up to 30. So you can have that extreme table. Right? That's clearly not independent, right? I think there's a big difference between those. But anyways, the Fisher's exact test enumerates all the possible tables and calculate the probability that you have your table or something more extreme towards complete, not independence. And there's commands in R to do all this. There's a density for a hypergeometric distribution, where you have to put in a bunch of things like the A, B, C, D, or some of those. Where'd I go? So there we go. The probability of this are 20. So this is our particular table. 10, 20, 10, 25, well, anyway, that's the table, ends up being that. This is choose is that combinatorics. You can do it in R, and it gives you the same value. And if we have 20, 10, 15, and 15 as our table, the Fisher's exact test gives us a p-value for testing whether it's independent or not of 0.2949. So it's enumerated all those particular tables and added up the probabilities. So if this is bigger than 0.05, we don't reject independence. So of our little example at 20, 10, 15, 15, what would we actually expect under independence? Maybe we can do something like this. So it's this total divided by this, so 30 times 35 over 60. 30 over 60 is 1/2, and 1/2 of this is 17.5. So we'd expect 17.5 and then 12.5, and then this has to add up to 25, so we'd expect 12.5. And this one's a little bit more, so it's 17.5 again, yeah. So this is our observed, and this is what we'd expect under independence. So it's not too terribly discrepant. We would not reject it. But if we started out with a table that's closer up to this extreme, 30 and 0, that thing's going to have a tiny probability. And there's a break point along there. That's the Fisher exact test. If we had 22 and 8, that gives a p-value of 0.03, so that would be rejected. 23, 25, and 5. So as it get closer to that 30, then the p-values go down, and you end up rejecting. So 21, is that rejected? So if we made this, if this was 21 and 9, and then we would need 14 and 16 to add up to the 30 and then the 35. That one would not be rejected. So it looks like once we get out to 22, so if we had the table, of 22, 8, and this would be 13 and 17, this table would look enough different from that, according to Fisher's exact test, to say it's not independent. Right? And it does look a little bit different. These are small numbers, but under the hypergeometric, those are the probabilities. Right. You can apply Fisher's exact test to bigger tables. Sometimes it takes a little while to do computing. Right? Because really big tables with big numbers, they have a lot of different tables to evaluate. This matrix was our data on the boys and girls. Right? The Fisher exact test here gives a p-value of 0.599. Right? It's not significantly different from independence. The smoking data gives a very small p-value, just like the chi-square test. It's not so surprising that these are similar to the chi-square test, because these are pretty big counts in those tables, and they're consistent with that. But it's pretty easy to do a variety of methods. And some are good for small tables. Otherwise, that chi-square test can be used. But any questions about doing different aspects of these things? So yes, there's the homework. Right? For those of you who came in, we kind of went over a couple bits of homework. 9 at the start, so that would be saved and be posted with the notes. So that's helpful to look at during the homework. You should take a look at that. And on Friday, we'll finish up a couple of other things in chapter 10.
Why is it called the exact test?
Exact probability calculation. It adds up the probability of those tables, and the chi-square is an approximation. Yeah.
The data set I
Okay.
wanted to use, I was having a hard time importing it into R. because it's really big. It's like 106,000. So I didn't know if
Okay.
there's a way to like make it smaller. I like cleaned it because it was from 1994 to 2014.
Yeah.
And so I like.
So something that size can read in. How many columns does it have?
It's 13 columns and 106,000 rows.
Okay. I mean, it should work.
Okay.
Yeah, I mean, it's just a larger object. It might take a little while.
Okay, so
to go.
because I did import and then I made it into an Excel sheet and I imported like we usually import
Yeah.
the other ones in there. It kind of like just seems like frozen, so we just get it a little longer.
Give it a little longer. I mean, if you want to send it to me, I don't know.
Okay.
You know, it's probably a couple megabytes. It might be.
Okay.
In an email, I'd be glad to look at it.
Okay, yeah.
See if there's anything particular about it. But I've had things, larger.
Yeah, that's what my
than
friend
that.
said. I was asking around. They said like they've had things that going in, so maybe like it was
Yeah.
just taking a while.
It might just take a little while. Or are you getting off the internet to read into that, or is it?
So I got it off the internet, but then I downloaded it and made it into my own Excel sheet. And then I even because at first I hid columns and I filtered
Uh-huh.
it or whatever, and I thought, oh, maybe since it's
That
so
tries
big.
to bring in the entire thing.
Yeah, so I I deleted some of the variables that didn't
Okay.
seem relevant.
They weren't gonna use it.
Yeah.
Okay. But in practice, it can do things that big,
Uh-huh.
but it might just take a little while.
Okay.
And feel free to send it, and I can try it.
Okay, awesome. I'm gonna try it again tonight, and if I can't get it, I'll
Okay.
send it to you.
Okay.
Thank you.
Yes. Hi there.
I have a question.
Yes.
So I want to know what's the relation between investment markets with the probability.
Like investment,
Yeah.
marketing,
Yeah.
type thing. So, so kind of in the field of investments and marketing,
Yeah.
right? I mean, they could use things from survey samples or data in a number of ways
Okay.
to try and predict who's going to buy different products, or sometimes they do clustering, so they take their customers and divide them into types,
Yeah.
right? And get kind of market segments, based on the age or the income of their subjects, and maybe they do a survey and get some data about them. Maybe they have their history of buying things, and then try to, predict who's going to buy. So marketing, right, becomes one thing.
Yeah.
Investments, like financial investments and like stocks and bonds
Yeah.
and things like that.
Yeah.
So they often can put very complex models to try and predict growth and the pattern of stocks, right?
Yeah. Yeah.
Right. So they often do time series methods to try and forecast.
Time series.
So like kind of the data over time.
Oh,
right,
okay.
yeah, to try and do those predictions. And often they're interested in error bounds, so getting standard errors of predictions and things.
Yeah.
So it gets used in, and many times there's very complex financial, different statistics that they compute to summarize things. And so I know in stocks, there's a series of the price that people are paying for the stocks, and that's going along.